Welcome to smooth parametric curves. So the idea here is in the XY plane, we can consider a curve to be smooth if it does not have a cusp. So to be smooth at a particular point, if it is continuous and has no cusp. So in terms of parametric equations, if F and G are continuous on I, and F and G are differentiable, are continuous on I and differentiable, on interval I, then the curve defined by the parametric equations x equals f of t and y equals g of t is smooth on I if f prime and g prime exist, I guess we don't need and differentiable. We can cut that out. We have that with f prime and g prime exist. And f prime, and there is no t such that f prime of t equals g prime of t both equal 0. So it's perfectly fine if either of one of those is 0 at any given point in time. We just don't want them to be both 0 at the same time. So for example, let's consider the curve defined by x of t equals t squared and y of t equals 2t cubed minus 3t squared. Our job is to determine when the curve is not smooth. So the first step is to find the critical values of x and y. So x prime of t is 2t. Y prime of t would be 6t squared minus 6t. X prime of t equals 0 when t is equal to 0. Y prime of t equals 0 when t equals 0 or 1. So this means that we do have one place where both x prime and y prime equals 0. So at t equals 0, x prime of t equals 0 equals y prime of t. And so the curve is not smooth. at these values. Of even more interest is the fact that x prime and y prime are changing sign at that point, and so now x will turn around and y, one of them at least is turning around. We get a corner. So this is how we can figure out. So step 2 is to identify any critical values that match, or identify any shared critical values. Again, we simply have to find where both are 0 or if one's undefined, etc. We can get our identify where the curve is not smooth. So if you graph this, we do wind up with a corner at t equals 0.